Edwin Hall. Okay, Edwin Hall in actually 1879. Okay, 1879, Edwin Hall has discovered this Hall effect. So what is Hall effect? So we will see this one. Okay, suppose if you have a current carrying conductor, suppose if you have a current carrying conductor, any conductor, semiconductor conductor, that means metals are, is mute, someone is unmuting always. Okay, this is three dimensional. I am just drawing. I don't know. This is so. This is some x direction. This is some semiconductor sample. Okay, we are taking this Hall effect can be observed in metals and semiconductors. So here we are taking some semiconductor material. This is semiconductor sample or material, whatever you take. Okay, along x direction, some current is going. Okay, along some x direction, some current is going. So here we will give the directions. This is y direction. This is z direction. Let's take this is z direction, and this is y direction. This is y direction. Okay. So just like it a bricks. You know brick, right? House building bricks. Just like you take a sample like brick type three dimensional. Okay. Somebody is saying in Telugu, I think. Ituka. Okay. So you take like that sample or okay, or metal or semiconductor. Here we will take a semiconductor material. Okay, along x direction some current is flowing in a semiconductor, some along x direction some current is flowing. So along z direction, along in this direction, along z direction we are applying some magnetic field. Okay, along z direction we are applying magnetic field. So what is happening, some because of this magnetic field there is a some Lorentz force. Because of this force or because of this magnetic field, the charges current flowing means due to charge carriers, right? Charge carriers, these charge carriers are deflected towards deflected from the straight path. Okay, this way electrons, suppose electrons are going in this straight path. So before, in the absence of electric field, sorry, magnetic field, once you applied magnetic field, these charges are deflected from the original path or straight path. Because always, you know, Fleming thumb rule, suppose if a current is going in this current wire, suppose some current is flowing in this wire, there is a magnetic field around this current carrying conductor, isn't it? Have you gone through this one? Or suppose if you take any magnetic, if lines are flowing this way, so there is a generation of current along the around the this magnetic lines of force. Or you can say, suppose some current is flowing in a wire, suppose in a wire there is a magnetic field around this wire. Okay, this is the you know, Fleming right hand thumb rule. This is the, can you see my thumb? I don't know. Okay, so in thumb rule, suppose upon is current carrying conductor, so there is a magnetic field. Or you can say this is a current, this is a uh, magnetic field lines are going, or this will be current carrying. Okay, current will generate, or induced EMF will create current, or vice versa. Okay, this is the Fleming thumb rule. Okay, so this is the thing. Suppose if a current is flowing in wire, there is a magnetic field will be generated. Or if you say this is the, you know, this one will come in basics only, intermediate only. So if a current flows in a conductor or in a wire, if you, there is a generation of magnetic field. Okay, that is Fleming thumb rule. Or here what we are doing, just like a current is going in a x direction, in a x direction, so we are applying some magnetic field along the z direction, along the z direction. So because of this magnetic field there is a magnetic force. Because of this magnetic force, these charge carriers will deflect from the original path. That means this charge carriers will deviate from the original path. Okay, that means what here? Okay, this is the three dimensional this one. Okay, so I'm drawing here. Okay, I don't know that is clearly. So this way some slab is there or sample is there, suppose. So here current is going, current. So we are applying along the z direction, along the z direction, this direction we are applying some magnetic field. So there is a, because of this magnetic field, upper surface there is a charge will induce upper face plus charges, down space minus charges. Because of the charges there is a some voltage will be generated. Because of this top surface and down surface there is a all voltage will be generated because of charge induced on the these surfaces. Okay, because see why these charges are inducing mainly. Suppose just I don't know, you clear these diagrams, I will draw it again, well, a little bigger diagram, then you will be clear. Just a second please. So just 1 second. So current is carrying along the x direction, and we are applying some magnetic field along the z direction. Because of this magnetic field there is a magnetic force. Okay, along this x direction, suppose this is x direction and this is the y, let's take a z direction. Okay, this is, let's take a y direction. Okay, y, x, y, z. So this always, you know, x and y and z are mutually perpendicular to each other, right? X, Y, Z are mutually perpendicular to each other. So along x direction some current is going. So we are applied magnetic field along the z direction. Okay, along the z direction. Because of the magnetic field, some of the charges will induce on the top surface along the y direction. Okay, on the front face, along the back face. Okay, because of the charge induced charges, because of this induced charges there is a voltage will be developed between this front face and bottom face. Okay, front face and bottom face. This developed voltage we are calling a hall voltage, or you can say this is hall voltage or hall field. Hall voltage or hall field. This is the hall effect. Okay, how, why these charges are inducing? Because of the Lorentz force, because of the magnetic force. Magnetic force always try to deplete the charges, from the original path. If there is no magnetic field, the charges will move along the x direction only, straight path. Once you applied magnetic field along the z direction, some of the charges will induce along the y direction. Okay, plus charges on top surface and minus charges on bottom surface. Because of the charges, because these charges induced on these places, there is a development of voltage, or there is a development of field. This voltage or field we can say hall voltage or hall field. Once there is a development of voltage, this field what that will do, this will restrict the further depletion of the charges. Okay, here magnetic field is there, some charges are depleting. After depleting from the original charge, there is a, after depleting from the charges from original path, there is a uh, hall voltage is developing between these two phases. This voltage protecting or restricting the further depletion of charge carriers from the original path. Okay, that is the hall voltage, and or you can say hall field also. This hall field, okay, this hall field or hall voltage, whatever you can say, hall voltage or hall field is perpendicular to the magnetic field and also perpendicular to the current. This like XYZ direction, hall voltage is developing along the Y direction and magnetic field we applied along the Z direction, and current is flowing along the X direction. So here like XY coordinate, this hall voltage or a hall field and magnetic field current are completely perpendicular to each other. So here main hall effect means if you take any semiconductor material or metal also, this Hall effect can be observed in metal also. So if current is flowing in x direction, suppose current is flowing one direction in a semiconductor sample or semiconductor material, so if you apply some magnetic field along perpendicular to the current along z direction or along y direction, whatever direction you can take, any direction, it's not a problem. Suppose if you can take current along the y direction or z direction, whatever you can take, it's not a problem. Suppose for convenient we are taking x direction. Suppose if you take any semiconductor material, in that semiconductor current carrying in one direction, if you apply some magnetic field perpendicular to the this current carrying direction. So there is a development of voltage or development of electric field perpendicular to the magnetic field and perpendicular to the current. This voltage and this field we are calling Hall voltage or Hall field. Okay, this is the Hall effect. Okay, Hall effect means after developing this voltage, after developing this voltage, okay, once we applied magnetic field, charges are decreasing, right? Charges are some charges, actually charges are going in this direction, x direction. So charges are depleting because of magnetic field. Once the charge is developed, once the charge is induced on the opposite faces, this field will restrict further depletion of these charges along the different direction, along the y direction. Okay, that is the use of Hall voltage. Hall voltage, what is the Hall voltage? What this will do, this will prevent further depletion of the charge carriers from the original path. Okay, mainly, so it is very simple. I don't know. Could you? I will explain again. Please listen. So we are taking any semiconductor material in 3 dimensional, okay, or a 2 dimensional, whatever you can take. So along the x direction, some current is flowing in a semiconductor. So that is okay. Okay, first point. So along the first one, along the x direction, current is flowing. So we are applying along y direction, some magnetic field is applying. Because of this magnetic field, there is a magnetic field means there is a magnetic force. Okay, because of this force, some of the charges are, some of the charge carriers will deplete, or charge carrier will get deflected, or change the direction. You can say change the direction from the original path, from the original path. Okay, that is the depletion, or you can say change the direction from the original path because of the magnetic force. Okay, once this depletion is happen, some of the charge carriers will induce on the front surface, and some of the charge carriers will induce on the back surface. Okay, so this is along the this is we have applied along the z direction. So along the y direction, charges will induce plus charge and minus charge on opposite faces. Okay, because of these charges we will get the some voltage is developing. This voltage we are calling a Hall voltage, or because of this charges we will have a electric field, right? This electric field we are calling a Hall field. Okay, Hall field or Hall voltage. After developing this Hall voltage, there is it will stop the charge carriers further depletion from the original path. Okay, this is the simply Hall effect. Could you follow this one? Are you, did you follow, or do you able to understand this one, Hall effect?
Yes.
So in this
Everyone.
electric field also will form.
Yes, sir. Yes. Okay, because electric field means what? Just positive and negative only, right? So you can take here positive charge is there, minus charge is there. This electric field always positive to negative.
In
This is
which
electric
direction,
field.
sir?
And
Electric.
also electric field is always positive plus charge to minus charge.
In which
Electric field
direction, sir?
line flows
Y-axis
always,
or x-axis?
yeah, along the y direction. So
Okay.
x-axis we are applying current. So and along z-axis we are applying magnetic field. So this Hall voltage or Hall field develop along the y direction. This Hall voltage or Hall field is always perpendicular to the current and also magnetic field. Okay, that is the thing. Okay, so electric field means always if plus charge is there, there is the electric field. Or you can write voltage also. You can write V by D. V is equal to E by D. You can write. Okay, this is suppose you have a plus charge, or if you have a battery, or sorry, 1 second. It is sometimes. So if you apply battery also, if you take any battery, the voltage developed between the two terminals, if you take, suppose if you have a battery here, if you have a battery, this is plus terminal and this is minus terminal. So developed voltage between these two terminals is V is equal to E by D. E by D, right? So here also same thing. If electric field is developing means there is a voltage also develops. If voltage is there, there is a electric field. Electric field is mainly due to charges. Okay, electric field also potential difference between two contacts or two terminals. That is the potential. Okay, potential means what? There is a difference between potential difference between two terminals. That is gives you some voltage. Okay, electric field due to some charges. Okay, because of charge, if charge is there, there is a lines of electric lines will be there. Electric forces are force of lines are there. This will gives the electric field. Okay, so here mainly, so Hall effect is what we are discussing is just a second. I will take new page. So here we are applying along the x direction we are applying current, and along the z direction we are applying some magnetic field. Okay, there is a development. Someone please mute. Along the y direction there is a voltage is developing. Okay, this voltage are electric field. Okay, this one we are calling a hall voltage or hall field. Okay, it is very very simple, just you understand properly, just listen carefully. So here we are taking a three-dimensional slab or sample. You can say sample or slab, or for example, if you have it small bricks at home, house construction bricks. Okay, that is also take as an example. Okay, this is the some three-dimensional sample. Okay, three-dimensional sample. Along the x direction we are applying current. Along the z direction we are applying magnetic field. There is a development of voltage between front face and back face, that is along the y direction, okay. This why this voltage is developing means because of the magnetic field, some of the charges, okay, current is going in this direction, right? So charges will deplete because of the magnetic force. Because of this charge depletion, we will have a some positive charge here and negative charge on the down. Because of this positive and negative, there is a hall voltage or voltage will develop. Okay, and also this is, you can say, hall field also. Hall field are generating or hall voltage is generating. This developed hall voltage will prevent further depletion of the charge carriers from the original path. Okay, that is the hall effect definition. Now we will prove the, we will see the how much voltage is flowing, how much voltage is developing, how much electric field is developing. We will see. Okay, now we know because of the charge carriers we have a electrostatic force, that is Q into E. Electrostatic force Q into E. Okay, let's take this one as one. And because of this magnetic field we have a some Lagrange force Q into V cross B. V is the velocity. Here we will take drift velocity. Okay, drift velocity means, suppose if a charge carrier is moving due to some electric field, that we are saying a electrons are drifted, or electrons are forced by a some electric field. Okay, if the electrons having some velocity by electric field, electrons are having some velocity due to electric field, that one we will say drift velocity. Okay, velocity of electrons due to electric field. Drift velocity definition is velocity of electrons due to some external electric field or some electric field. Because of electric field, electrons are getting some velocity. This is the drift velocity. We'll see drift and diffusion process next tomorrow class. Okay, further today this is a simple definition: velocity of electrons due to electric field. Once you electrons are getting some velocity due to applied electric field, that is the drift velocity. You take here Vd. Okay, so here you expand cross product Vd into B sin theta. Vd sin theta. So electrons are moving along the x direction, right? Along the x direction. So we are applied magnetic field along the z direction. So x and x direction and x coordinate and z coordinate is always perpendicular. So this cross product, what will be the cross product now? What is the theta now? What is the theta value? So charge carriers are moving along the x direction. We have
90
applied
degrees.
Yeah, 90 degrees. Magnetic field along the z direction. So theta is always 90 degrees. Here if you substitute theta 90, so this will become 1 QDB. Okay, right? So now equation 2. Okay. Now at equilibrium condition, that means when forces are equal, there is no other forces. Okay. At equilibrium condition, if you take, so these two forces are equal. QE is equal QVD. QVD B. Okay. This Q key will cancel, or you can take here E also, because charge of the carriers is E. You can take E also. It's not a problem. So E is equal to here VD into B. VD into B. So here, see, so this voltage, this field we can take Hall field. You can take this one Hall field VD into B. So this is equation. Let's take 3. But we know this current density J is equal to N into E into VD. So this is the drift velocity, the relation between current density and drift velocity. We have one relation. Tomorrow we will discuss this relation. Okay, we will discuss tomorrow drift and diffusion process. These two processes are very important for PN junction. This we will discuss tomorrow. But at present current, the relation between current density J means current density, current per unit area. Current density means what? Here current per unit area, and N is the carrier concentration, E is the electron charge, and VD is the drift velocity. So we know this relation. From this relation you can write VD is equal to J by NE. J by NE you can write. So here you substitute this VD in equation 3. You substitute, simply substitute VD is equal this one. Okay, you write EH is equal. Now what is the expression? JB by NE. JB by NE. This voltage, this field is Hall field. Now you can write this expression. EH is equal RH into JB. RH into JB. This RH is equal to what we can write? 1 by NE. This is RH is all coefficient. All coefficient. Okay. Coefficient. And this EH is the Hall field. Okay. EH is the Hall field. Okay. All field. EH is all field. And from there, just what we have done just replaced the drift velocity with using current density and drift velocity relation. Vd is equal to J by Ne. Okay, just you substitute here 1 by Ne is equal to, you can write RH. 1 by Ne is equal to, you can write RH. So this is RH is Hall coefficient. Hall coefficient. This is for, okay, this is for electrons. This is for electrons. If you same thing if you derive, okay, RH is equal to 1 by PE. 1 by PE. So this is for holes. This is for holes. So electron charge is negative, so you write here minus. For electrons, Hall coefficient is always minus 1 by Ne. For holes, Hall coefficient is 1 by Pe, because hole charge is positive and electron charge is negative. So this is the Hall coefficient and Hall field. So what is the how you can write the Hall voltage from this expression? Suppose if you have a sample thickness D, sample thickness is D. Here we have positive charge and here we have negative charge. Okay, because of this positive and negative potential, these charges are separated by distance D. There is a electric field will be, that is equal to EH by D, right? EH by D. So here EH is equal to, you simply substitute here, you simply substitute VH into D, right? V is equal to, is this formula right? Is this right? Hmm? Are you listening?
Yes, sir.
Is that formula is right? VH is equal to E by D I have written. Is that correct formula? No. V is equal to ED. V is equal to ED. Okay, simply if you want EH, okay, VH by ED. Just I am written VH by ED. You substitute here in this place. Okay. Suppose this is a Hall field. Suppose you want Hall voltage. What you will do? You substitute simply VH by D in place of this one. Okay, VH by D to RH into JB. RH into JB. From this expression, you can write VH is equal to RH and JB D. D is the thickness of the sample. Thickness of the sample. Okay, this is the Hall voltage expression. Or you can write VH is equal JBD by N1 NE also you can write. This is okay. This is enough. Up to here it is enough. Okay. This is a Hall voltage. VH is the Hall voltage. EH is the Hall field. Okay. Hall voltage. Okay, right? So very easy. Just we equal two equations. Just we equal two equations. From there we have derived. Just I will derive again. Please listen carefully. So magnet electrostatic forces due to electrostatic forces Q into E. Q into E, and we know because of magnetic force there is a large force or magnetic force, that FL is called Q into V cross B. Okay, V cross B. Here you expand cross product. Here you write VD. VD is the drift velocity. Electrons get some velocity due to electric field. Okay, B into sine theta. So this magnetic field and electron direction, electron movement is electromagnetic field is along the z direction and drift velocity along the x direction. So this x and z always perpendicular. So theta is always 90 here. So that means Lorentz force equal to QVD into B. Okay, QVD into B. So equal 1 and 2 expressions at equilibrium condition. These two forces are equal. Okay, these two forces are equal. Okay, or you can write electromagnetic force Q into E plus V cross B. This is electromagnetic force, right? This are also you can write. This is first term is electrostatic force, second term is electromagnetic force. That way also you can write. This way also you can write. So you are equal 1 and 2. If you equal this 1 and 2, Q is equal to U and QVDB. Okay, from this expression, Q key get cancelled out and E is equal to here, E is equal to VD into B. VD into B. Here E means Hall voltage. Hall voltage. Now we know current density and drift velocity relation. J is equal to NEVD. N means carrier concentration, E means electron charge, J means current density, current for unit area, D means VD means drift velocity. So here VD is equal J by J by NE. From this expression, just we will replace VD or EH is equal JB by JB by NE. Or you can write here V is equal to ED, right? V is equal to ED, we know that expression. EH is equal to, you can write VH by D. VH by D. D is the thickness of the sample. VH is the Hall voltage. EH is the Hall field. Okay. If you replace this one, VH is equal to JBD by NE. JBD by NE. So or you can rewrite this expression. Okay, or you rewrite this expression, or you can write this expression also. EH is equal to RH into JB. Okay, here RH is equal to 1 by NE. This is RH means Hall coefficient. So here also you can write same thing I am writing. So replace 1 by E with RH. This is Hall coefficient JB into D. Okay, this is also Hall voltage. Here RH is equal to 1 by E. For suppose if you take electrons, 1 by Ne for electrons. 1 by Ne for electrons, because electron charge is negative. So if you know RH is equal, if you want to derive for holes, you can derive it same process. So here 1 by Pe for holes. Okay, here holes charge is positive, so this RH is positive. This is Hall coefficient. This experiment you have also. Suppose what is the use of this Hall effect? What is the use of this one? Mainly, so what is the use of this Hall effect? What is the use? Please, anyone? What is the significance of this Hall effect and all voltage are feed? What is the applications, or you can say what are the applications? Please see the answer and tell me what are the applications. What you can find out using Hall effect. What you can find out? What can you find out? Don't see the what I explained. See that equation and tell me what can we find out using Hall effect. This experiment you have intermediate also, isn't it? At least are you there?
Yes, sir.
Only one is there. Remaining all are absent. Are you not listening at all?
Yes, sir. You're on.
So see, just see the here you see this expression. See, RH is equal to 1 by NE we have written. RH is equal 1 by NE we have written. So in this expression you can find out carrier concentration. Suppose how much carrier concentration is in semiconductor. Or if you write 1 by PE, you can also estimate PE. PE means carrier concentration of holes or density of holes, density of electrons. Also you can calculate, you can estimate using Hall effect. And many very important thing is, suppose I have given some material to you. Okay, some material to you. I don't know this is P type or N type. How you will estimate using Hall effect? Suppose we don't know anything about. I given some material to you and I asked you whether it is P type semiconductor or N type semiconductor. So you have to perform Hall effect. You have to first thing take the material and take the sample, and you have to perform the Hall effect measurement. Hall effect measurement, Hall measurement. Once you do the measurement, suppose you calculate depletion, this coefficient, Hall coefficient. Suppose you get 1 by NE. Okay, 1 by you calculate N and E. So if you get negative value, that is N type semiconductor. Okay, that is N type. If you get RH value negative, that is N type semiconductor. If you get RH positive value, that is 1 by P. That is if you get positive value, that is P type semiconductor. Suppose just I gave you one in one material or thin film or sample, whatever you can say. So I ask you to find out which type of semiconductor it is, P type or N type. So you have to measure the Hall coefficient or you have to perform the Hall effect. From there, if Hall coefficient is negative, that is N type semiconductor. If Hall coefficient is positive, that is P type semiconductor. That is the main use of Hall effect is you can estimate the, you can find out the type of semiconductor, either n-type semiconductor or p-type semiconductor. And also you can estimate the mobility. Mobility is, we will discuss this one. Mobility means how fast electrons or how fast holes are moving in a semiconductor. Suppose electrons are there in a semiconductor or holes are there in a semiconductor. So how fast these electrons are moving one place to other place. Mobile means flexible, right? Moving freely, it will move. So this will indicate mobility means how freely or how easily these electrons and holes are moving one place to other place. This is also you can write sigma by Ne for electrons. You can this one also using sigma is the conductivity of sample. Conductivity, sigma means conductivity. Okay, conductivity. Okay, so using this formula you can estimate mobility of charge carriers for holes or electrons you can estimate. Okay, these are the few applications. And okay, and also you can go through Google, you can find out many applications. Tomorrow we have a small portion. Someone asking doubt or someone asking doubt. So this is the Hall effect. So could you follow today class? అర్థమైందా లేదా?
Yes.
At least
Yes, sir.
very